Hello. Okay, so I have some new headphones. I hope this will sound better and record better so you can hear it. Okay, so let's start with the warm up. I hope you're doing well. I miss seeing you. Would you start by doing number 9 on set 143, writing a third degree Taylor for sine about pi over 6. I'll give you a second. Feel free to pause it at this time and do that. And when you're ready, hit play again and we'll move on. All right, so whether you write the general every time, at this point you might not be, but this is the plan. And we're going to keep that going through until we get to the third degree. Remember, degree means power, not number of terms. All right, so f at pi over 6 is sine at pi over 6, which is a half. F prime at pi over 6 is cosine at pi over 6, which is root 3 over 2. I'm starting to see the pattern here, so I feel like my Taylor is going to be a half plus root 3 over 2 x minus pi over 6 to the first over 1 factorial minus 1 half x minus pi over 6 squared over 2 factorial, that's f double, minus root 3 over 2 x minus pi over 6 cubed over 3 factorial. That's the third degree Taylor. And yeah, that'll do. I think that's good. All right. Would you then get out your notes for set 143 and let's see how 143 goes, the binomial theorem. First, let me get my notes in line. All right, so the idea of the day is binomial theorem. Now this is binomials, which you did a lot of in the green book, but as applied to series. So for example, if you were asked to create a Maclaurin series for 1 plus x to a power. Now, if you're like I was, then you're thinking, what's the point of that? If you were doing 1 plus x to a power like 3, and I expanded, isn't that already a polynomial series? Why would I make a Taylor series for something that's already a polynomial series? Well, think instead more like fractional powers, like 1 plus x to the half. That's really why we're going to use a series for that, for something that's ugly in that way. All right, so if I were to do this, then because it's Maclaurin, that implies center equals 0. So I need to start by finding f at 0, which is 1 plus x to the p evaluated 0, and that's 1. F prime at 0 is p comes down, 1 plus x to the 1 less power at 0, and that's p times 1 plus 0, so that's just p. F double at 0 is p times p minus 1 comes down, and the power drops to p minus 2 at 0, which is p times p minus 1. And F triple, I think, will be enough. P times p minus 1 times p minus 2, 1 plus x to the p minus 3 at 0. And you can see then when 0 goes in for x, it's just p times p minus 1 times p minus 2. And so on. We could continue, but I think that'll do. Excuse me. So now, the Maclaurin might look something like f at 0, so 1 plus the derivative, p times x minus 0, so I guess I don't need to write that. Instead, let's just write x to the first over 1 factorial plus p times p minus 1 x squared over 2 factorial plus p times p minus 1 times p minus 2 x cubed over 3 factorial. And then the general term is a little gross because the derivative could have lots and lots of factors. Now that's okay. Let's start off with, we know it would start with p times p minus 1 and go to p minus 2, and we would continue to get factors here until we got to the last factor. Now, if you look for the trend here of when it ends, it looks like there that p minus whatever is 1 less than the last power, and that seems like it's true too, p minus 1, which is less than 1 less than 2. So, tell me, what would it be ending at? P minus, and it seems like it would be 1 less than the power of what we ended at, x to the n. So, that's the general term. Pretty gross. There's a little cleaner way to do it we'll talk about on the back. Our book doesn't say it, but we will. All right. Now then, let's talk about how to use this. Say I wanted to estimate the square root of 1.25, and I want it with great precision, error less than 1,000th. Well, first we would have to create a Maclaurin series and figure out what function am I going to even try and model. So you want to make it a binomial. It's not the square root of x. That's not a binomial. Binomial means 2. You want it to be always 1 plus something to a power. Making that 1 is a bit of a stinker sometimes. It's kind of like our tangent. We'll talk about that on the back side. So if I were to try and do this up top, this looks like what I did up there with a power of 1/2, yeah? So my Maclaurin might be something like 1 plus, instead of p like we had above, it'll be 1/2 x to the first over 1 factorial. And then it's 1/2 times a power less, so negative 1/2 x squared over 2 factorial. Then 1/2 times a power less times a power less than that, x cubed over 3 factorial. And we continue on doing 1/2 times a power less times a power less, and continuing on till it was p minus n minus 1. And in this case, oops, p is 1/2. So 1/2 minus n minus 1, x to the n over n factorial. You dig? So then, what about the square root of 1.25? Well, the square root of 1.25 is like 1 plus 0.25, which, if that's the function with 0.25 in it, then I can model that with the Maclaurin of 0.25 in it, which would mean putting 0.25 in for every x. So 1 plus 1/2 of 0.25 to the first over 1 factorial, plus 1/2 times negative 1/2 times 0.25 squared over 2 factorial, and eventually 1/2 times negative 1/2 times negative 3/2 times 1/2 minus n minus 1 times 0.25 to the n over n factorial. And I imagine that would converge pretty quick, because 0.25 to greater and greater powers would get smaller and smaller. Then you got the fractions and the factorial division. It would get small fast. It would converge quickly. And we'd probably get pretty small error bound. Excuse me. All right. Oops, I guess I did that there. Sorry, I decided what x I'd use, and that is an x of 0.25. Now, as far as getting an estimate less than 1,000th, it does start to alternate after term 2. You can see that after term 2, you'll start to get a negative, then a negative times negative, so a positive, and you'll keep getting alternating negatives, so you can use error bound. We need to figure out which is the first term less than 1,000th, And because later on we're going to actually have to find that sum, I would strongly recommend you store as you go. So if I start with 1/2 times 0.25, that's probably not less than 1,000th, but I am going to store it to A. Now, you can keep retyping as you go, that's fine, but it's a little more expedient to take what you had and then bring in what's new. So you can see that in going to the second term, we then multiplied by -1/2. Oops, or not. Strangers in the night. And the 0.25 got squared. And then we divided by 2 factorial, which I know I don't really need the factorial, but all right. Now that was not less than 1,000th. And that's kind of wacky. I don't like that. Sorry, I think I made a mess of this. Apologize. So what I'm going to do is create a big old fraction. And then create another big old fraction. Oh, yeah, 1, 2, -1, 2, sorry, 0.25 squared over 2 factorial. All right, I feel like that's good. So I got -0.007. Now that's not less than 1,000th as far as absolute value goes. So I'm going to store that because, again, I'll need that later to be. But now I'm going to recall and find the next term. So a couple changes. First of all, I'm going to change the exponent to 3. And second, I'm going to add in a new fraction of -3 over 2 and change the denominator to 3 factorial. Then I get 9 times 10 to the -4th, which is 0.0009. That is less than 1,000th, so that seems like that's my error bound, and I'm ready to go. So I found that the 1 to the 3rd, which is A4, is 9 point something times 10 to the -4, so that'll do. So in terms of finding my answer, to find the actual sum, I'm going to look at the sum of 1, 2, 3 terms, and that'll be my estimate, and my 4th will be my error bound. So the square root can be approximated by sum 3, which is 1 plus A plus B, and I get something like 1.1171. there in this estimate is less than 1,000, well, let's justify it because this is an alternating series, and when I say this, I mean the series with the 0.25 in it. This is an alternating series. The limit of the terms is definitely 0, and the terms definitely get smaller. So it must be the case that the difference between, let's call it this, the square root of 1.25 and my estimate of 1.1171 is, which is the same as the true infinite sum and S3, must be less than or equal to A4, which is 9. I can't remember what it was. 9.765. 9.765 times 10 to the negative fourth, which is less than 1 times 10 to the negative third, or 1,000. So, I got my estimate, and if I were to check it, the square root of 1.25 is, if I were to subtract here, the difference between these is less than 1,000. All right? If you subtract 1.1171,875, you can see it is coming in less than 1,000. All right, so there's a darn good estimate, and I mean a really exact estimate of a square root. And let's move on then. So this will be a little bit of review of pre-calculus / combinatorics. If you take a combinatorics class or in college, it's pretty cool. You'll love it. So if you remember, we talked about how many different ways can seven people be arranged in 3 seats. So let's start. If I taught this pre-calculus, I would say let's start with imagining all 7 people were arranged. If I arranged all 7 people in order in seats, it would be 7, 6, 5, 4, 3, 2, 1. But if I only had 3 seats, then after I arranged the first 3 seats, I wouldn't say, well, let me arrange those people that are getting left out. I would eliminate that. Now that's a permutation, and another way of looking at that, besides putting these spaces down, is saying I could arrange all of them, but remove the ones that are not chosen, which is to say 4 factorial. Generally speaking, you'd say this is the total to choose from and the not chosen arrangements, because we're not going to arrange people not in the group. Now, if I said how many different groups of 3 can be made from 7 people, this is assuming order matters. So I have 7 different people I could put in that first seat, and I want to count them different depending on arrangements. But if I talk groups, then I want to remove the ways that once I have those 3 people, I could rearrange them. So that's further remove them from what I've already done. Now, I already know that the number of possible permutations where order matters is this. And now I want to further remove the ways to arrange 3 people. Well, how many ways are there to arrange 3 people in the seats? Well, that's that guy, 3 factorial. Now, that's a combination. And there are several notations for that. There's this or this. And I'll use the other one. I will often say that as n choose r. That's how it's frequently spoken. And it's combination notation. The general formula is building off of this. You would say it's something like the total of all things arranged, and you remove the ways to arrange those not chosen because we don't want to order those. But in groups, you also rearrange those or remove the ways to arrange those that are chosen. So you'll often see this written as n factorial over n minus r factorial r factorial. And that's, again, a way of finding combinations. All right, now, what does that have to do with series? Well, we'll talk about that here. If you remember back in the day, again, binomial theorem, a plus b to the first is a plus b. And a plus b squared is, you say it, good job. And what about a plus b cubed? Do you remember your cube expansion? It is a cubed plus 3a squared b plus 3ab squared plus b cubed. Now we can find the coefficients by Pascal's triangle, but combinations are another way of finding the coefficients. So a good question would be, why combinations here? I thought that was more of like a counting idea. Why use combinations? Well, consider it this way here really quick. Say I was doing a plus b cubed. Well, a plus b cubed means a plus b times itself 3 times. Now say I multiplied this and did not simplify as I went. So say I went a times, now let's do these first. So if I expanded that, then it would be AA plus AB plus BA plus AB. I could then multiply that by A plus B, and I get something like AAA plus AAB plus ABA plus ABB plus DAA plus BAB plus BBA plus BBB. All right, now, can I simplify? Well, you say, can I simplify that? Well, that's 2 A's and a B. Can I combine it with that 2 A's and a B? Or that 2 A's and a B? And I'm sure you are right now saying, of course, Mr. Rickman, you can combine those because they're like terms. Order doesn't matter. And that's exactly right. Order doesn't matter. There are 3 different groupings of 2 A's and a B. Likewise, there are 3 different groupings of 2 B's and an A, and 1 grouping of 3 B's. So it's all about groups, and order doesn't matter in multiplication. Now, if you were to write this then in summation notation, which would be logical because it is, after all, a sum, then you might say something like, this is basically 3 parts each time. A coefficient, an A, and a B. Well, let's start with the B coefficient. The B coefficient is usually the place you start because it's most likely tied to the summation. When you do a summation counter, it counts up by 1 each time. And that's exactly what B does. The B power counts up by 1 each time. So let's call the counter variable, I guess we'll call it n. And what does n start at? Well, I think you can see it starts at b to the 0, so n must start at 0. And what does n end at for this problem? In this case, n ends at a power of 3. What about the a power? Now the a power counts down, but remember that each time the powers always add to the total power in the problem. So in a cube, the powers always add to 3. So in this case then, the power of a would always be 3 take away whatever the power of b is. And then the coefficients. Now, we talked about the coefficients being combinations of 3. Choose whatever the power of n b is, yeah? So, for example, this guy came from 3 choose 1, which is 3 factorial over 1 factorial 2 factorial. That's how we get a 3. This came from 3 choose 2, which is 3 factorial over 2 factorial 1 factorial. So combinations, all right? Now, generally speaking, if instead of a plus b to the third, I said a plus b to any power, then it would still be 3 components. A combination, an A and a B. Now the B is still tied to n, starting at 0. And as far as the ending power, rather than a 3 here, it would go to whatever the total power might be. You'd go until you got to the final power. And as far as the a power goes, well, it's always the total power, which in this case now is p. Take away the power of b, so p minus n. And then the combinations. It's always the total power, choose the power of b. That's the binomial theorem, and it gets you any kind of terms of a plus b to a power. If instead I looked at it as 1 plus x, then it would be more like 1 plus x to a power. And instead of a, you'd just have a 1 and x to the n instead of b, and p choose n here, yeah? Simplest possible form. P choose n, x to the n. Now it's starting to look like a Taylor series. All right. Well then, here we go. Say I talked about, rather than that expanded gross p times p minus 1 times p minus 2 times dot, 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 dot stuff, let's look at this in a little more formulaically. To fit 1 plus x to the p to any power, which could mean roots, I'm not going to fit a square root graph with a polynomial unless I make it lots and lots of powers so that it can behave like that. So you would need to add infinitely many terms, not just a finite number of terms, but infinitely many terms, which means that instead of the binomial just ending at p, then it would be more like going infinitely many. But it's still x to the n and total power choose n. And I remind you, that combination is total power over n factorial and then the difference between the two factorial. All right, now let's see how this goes with the front of the notes. When n equals 0, I get something like p choose 0, x to the 0. P choose 0 is p factorial over 0 factorial p minus 0 factorial. And that's 1. Well, that is p factorial over p factorial. 0 factorial is 1, and so we get a 1 for the first term. When n equals 1, I'd take p choose 1, x to the first. Again, p choose 1, or combinations of p things taken one at a time, are p factorial over 1 factorial p minus 1 factorial. If I clean that up, though, imagine how that would cancel a little bit. So if I took p factorial and broke it up into p times p minus 1 factorial, then p minus 1 factorial would drop away, and I would just be left with p. If n equals 2 goes in, then I'd have p choose 2x squared. And combination-wise, that would be p factorial over 2 factorial p minus 2 factorial x squared. But again, trying to imagine what the combinations or the factorials would drop out as, I would take the p factorial and strip off factors until it could cancel with p minus 2. Now when I did that, I would strip off a p and a p minus 1 until I got to p minus 2. So I would have p times p minus 1 over 2 factorial x squared. You can see then that you're starting to look a little like we had yesterday. If we had, let's go for the general term, what the heck? So the nth term would be p choose n, x to the n. P choose n would be p factorial over n factorial p minus n factorial. But I would, in order to cancel out p factorial with p minus n, I would have to strip off p and p minus 1 and p minus 2 and keep stripping off until I got to the one just above that, or one less than that, excuse me, and then p minus n factorial. And you can see then that that is, in essence, what we had yesterday. All right, so it's just so much easier to write that with a combination than this big dot, dot, dot mess. It's terrible. Last but not least, and we're going to have to come back to this because this involves a substitution skill we have to talk about still, but we're almost there. So if I wanted to estimate the square root of 26, the problem is that it's nowhere close to 0, and 26 is so far away from 1. If I wanted to estimate the square root of 26 using the function 1 plus x, that would mean I have to use an x of 25 in my Taylor, or in my binomial series, in my Maclaurin. And an x of 25 would be something like 1 plus a half of 25 plus a half times negative 1/2 times 25 squared over 2 factorial. Now, you can see the big deal with 25 is it's so big that it's going to take forever before I start to see these converge, and it's going to be forever before the factorials eventually catch up and overcome the 25 to bigger and bigger power. So it's going to converge, but so slow. It makes estimating it really poor and terrible. So instead, we could start with something like f is 25 plus x. We could make the 1 by factoring out 25. Oops, factoring out the 25. Then it would be 1 plus x over 25, yeah? Take out the 25. And then do a binomial on that with a bit of a substitution of, okay, now in this case, do you agree that x would be 1? And it would still be 1 all the way throughout here. So we could use a series with an x of 1, and that would be equivalent to the square root of 26. And I just forgot my square root, yeah? All right, so just so we're clear, this would be 26 25ths, which if you then simplified, it would be root 26 over 5. The 5s would cancel. It is equivalent to root 26. The idea is that we could expand the root in there with a binomial series. We could use the binomial with an x of 1/25. And so it might look something like 1 plus, instead of p, the p is a half, and 1/25. And I could do a half times a half, negative a half, excuse me, 1/25 squared over 2 factorial. Now that alone would get me a pretty good estimate right there, and I could continue going on, adding terms and getting a better and better estimate. You would see then we could get converging much faster than if I tried to use 25 as the x value. It would take forever. Now this involves substitution. We'll talk more about that later, but that should get you going. Tomorrow is extra practice. This will take a while to get good at. You need to be patient. I know you guys are used to being awesome right away, but these do take practice. So persevere, and they'll gradually get more and more simple, all right? Thank you for watching. I appreciate that you're watching these and not just blowing it off and going outside and having fun like you might want to. Thank you for all you do. I appreciate it. Have a good day.